Okay.
All right. So this is Rudy Rucker. I'm here with Stephen Wolfram, and we've been meaning for years to make a podcast. So
this is our chance.
This is it. We're here at a conference in Miami Beach. Maybe I'll just mention how I met Stephen. He wrote an article in the Scientific American, and I think it was around 1985.
84, I think.
84, yeah. About cellular automata. And he had discovered or formulated these two principles, the principle of computational equivalence, that basically anything that looks like it might be doing a computation, if it's not doing something kind of trivial, then it's probably a universal computation. And then the other one was the kind of more interesting principle of computational irreducibility, is that most interesting, and I call them gnarly computations, Stephen calls them class 4, I believe, and processes, they're doing something, like if you look at a waterfall and the little ripples moving along the edge back and forth, or a dripping faucet, or a leaf fluttering in the wind. In a way, those are computations, but we can't ever predict. There's no easy way to predict them. And maybe you could say something, Steve. Why is it that people refuse to understand these things?
I think paradigm shifts are hard. It's fascinating. I've studied the history of science a lot, and I've looked at, lots of paradigm shifts that happened in the past. And from us today, 50, 100 years, 200 years later, it looks like everything happened instantly. But really, that's not how it works on the ground. And, the time that it's been since I first started looking at these kinds of things, 35, 40 years, it's actually a very short time in the history of shifts of this type. And I think what we see, the big thing that I've been excited about is a very silent revolution, which is, for exact science for like 300 years was dominated by this idea of take the world and write down an equation for what happens in it. That was kind of that was the big thing that worked in physics. It's the big thing that led to a lot of our engineering practices and so on. Well, that's been dominant for 300 years. In the last probably 10 to 20 years, we've seen a transition, and when people make new models of things, whether it's behavior of people on the web or whether it's some other kind of even physical system, they're using programs as the basis for those models, not mathematical equations.
Right.
And so that's sort of step one, is what's your foundational modeling methodology. Step two will be that, okay, given this new foundational modeling methodology, what are the basic phenomena that you see in those kinds of models? And computational irreducibility, principle of computational equivalence are, hit you very hard when you're using those modeling methodologies.
Let me say a little more about that principle. A lot of people won't know what it means. It's also, in a way, it's related to Turing's halting problem, which is if you have a given computation, you can't just by looking at it tell if it's going to run forever or if it might reach some terminal state and stop. And the variation on that is that most computations that are doing something interesting, there's often no way to speed them up. And when we talk about speed up, we don't mean like shaving it off by like a factor of twice as fast, but like by getting twice as good a computer chip. We mean of some radical speed up, like the way if you're adding two numbers, if you put them into Arabic numeral notation and you use a little algorithm for adding, that's a lot faster than adding them by making that many marks on a log and then counting them. It's exponentially faster. And those are the kind of speed ups that people dreamed that they would get some formula to human behavior. There was this dream among AI people for years that there was some simple formula that was going to give us the secret of AI, some simple insight. And now it looks like we're just going to have to beat the problem to death with deep neural nets, training them.
Yeah, I think that's, in the end, what that's telling one is AI isn't actually as hard as we thought. Because really, you can take any old crazy thing and you bash it hard enough and it will show behavior that is similar to the behavior that we're used to seeing in the one example we have of intelligence, namely our brains. I think also I'm excited about an aspect of that, which is this is a place where we're we're going out and just getting these programs out from the sort of universe of possible programs, and then we're saying, here's my AI thing, my image identifier, my speech recognizer, whatever else. It's not a program that we step by step constructed, like we're used to doing with engineering. It's a program that we just sort of went out and captured in the universe of possible programs. Now, I've been interested in kind of what's out there in this universe of possible programs. The deep neural net case is a little bit of a special case because we, like biological evolution, we're kind of progressively optimizing these programs rather than just going out into the wild and just finding one that's.
Well, the training, that is an interesting thing. Again, a lot of people aren't familiar with that, and a neural net is, it's kind of a bunch of nodes, and then there's imaginary lines between them with weights on them. And you just train it with data, and if it gives the right answer, you intensify those links, and if it doesn't, you change the links. And it's very time-consuming. But, evolution was very time-consuming. It took millions of years, and it ran on the whole surface of planet Earth. So there was this dream we could just go ahead and get some puny little chip and put some insight on it, and we'd have AI.
Yeah, but I think what we're seeing with the neural net business is neural nets are learning things that us humans are able to do in the world that us humans are used to inhabiting. Mm-hmm. If we asked, can one of these neural nets be trained to solve some mathematical problem that's not something we're used to in human experience? The answer is no, not so directly.
Not at this point.
It's. What we're seeing is that it's kind of a way of. It's like we might sort of describe some building using some architectural design program where we say it consists of this basic roof shape and this basic shape and so on. We get to give these fairly small descriptions of things, and that's kind of what these neural nets are keying into. Right. Is that they're giving us a way to sort of give an approximation to the way that the world is set up, but it only works when the world is set up in ways that are similar to the ways that we're used to. So
right. At present, they're really just learning to imitate us. There's another kind of aspect of this whole thing. If you think of nature as things being like computations. I never want to say, sometimes people make the mistake of thinking if nature's a computation, that means we're living inside a virtual reality on some big computer. But that's, the big computer is the universe. There's no reason to try to squeeze us into some beige box in some basement laboratory. But it gives me more of an appreciation of the natural worlds. And part of it, there's the ideas of chaos theory are kind of related to the things that Stephen talks about, that if you look at a leaf waving in the wind, it's not random, but on the other hand, it's not predictable. And that whole thing, again, that's something the average person has trouble grasping, that there are things like that. They're deterministic, but they're not predictable because they're so computationally rich. And that's, I find it very beautiful to see these things. I think, though, that's a slightly different, the official chaos theory idea is, it's like when you flip a coin, the way it's going to come out is going to flip in the air a bunch of times, and which side it lands on depends sensibly on precisely what speed it left your hand with. Well, that's I don't find that a very interesting view of chaos, because that's
that was the sort of original notion.
I know that's one of the ways that they talk about it.
Right. The other notion is more like when you compute the digits of pi. It's 3.1415926, and then I pretty much run out of memory. But there's an algorithm for computing those digits. Yet once you've computed them, they seem, for all practical purposes, completely random. I think that's the more interesting sort of computational irreducibility type of source of randomness that we see. That is, it's an intrinsic randomness that's being generated just by a computational process.
Yes.
It's not just, we didn't know exactly how fast you're going to flip the coin, so we didn't know how it was going to come out. It's that the actual dynamics of the process are themselves intrinsically generating randomness. Mm-hmm. And that's, in a sense, that's this whole kind of idea of computational irreducibility. You have to actually compute to know what's going to happen. Yes, I like that.
I think about that when I'm writing a novel, that, sometimes people say, well, do you outline what you're going to write? And I'll do a rough outline, but I can't. If I could predict where the novel was going to end up, then it wouldn't really be worth writing.
Because that's fascinating.
Yeah.
I mean, I don't know what the writing process is for something like fiction. So you're watching the novel unfold through the actual act of writing it. So
right. I can't produce it any more rapidly than to write it.
Oh, that's very interesting.
Yeah, I mean,
right. So you're living the characters, so to speak. You're living whatever is happening in the novel.
In a way,
have to live in the actual production.
Yeah, because it's such a complex computation. It's as hard a thing as I can do, and I can't suddenly be 10 times smarter and predict what I'm going to do. I just have to do it.
Yeah, I think of course, I always view the fiction business as it's sort of, you have it so easy. You just have to invent stuff. In my kind of world, most of the time, if I'm doing science, at least, I have to kind of fit in with the way the world actually is. So
well, that's why it's a relief to go from mathematics and computer science to writing science fiction. Because if I need something to happen, it's just bam, there it is. But
in a sense, there's, I mean, you presumably have to have the constraint of some kind of, it all has to fit together, it all has to make sense.
Right, well, the more constraints, the better. I mean, I like to have it be rigorously logical, because I do have that mathematical background. So I have the assumptions that I've made, and I spend a lot of time working out, what could happen. And there's this thing that happens that when I'm doing that, I'll see things that I hadn't thought of that could happen, but that follow logically from this situation. And then that gives me ideas for things.
But of course, when you're writing people, there isn't a logic, in a sense, to the way that people don't operate according to kind of, the propositional calculus logic.
Well, they operate in ways that are in some sense logical, but they're not like deducing things. I mean, people like to fly off on tangents, and there's the whole emotional thing. And you like to say you're going to describe the whole world in the Wolfram language, but that's not exactly true if you're describing the way people act,
It's an interesting point. I mean, well, by the way, this whole computational irreducibility thing has a lot to do with, I think, this process of people working out what they're going to do. I mean, this is, we think we have free will because we can't readily foresee what we're going to do.
Exactly.
We have to kind of go through the actual process to decide what we're going to do, and that's kind of computational irreducibility kind of reaching us again. But no, in terms of this question of whether to what extent can we describe the world symbolically? To what extent can we figure out everything about the world? I think the thing that my point of view is there is a set of things that are possible in this sort of, we can set up rules about the world, and the world will then behave in all kinds of complicated, computationally irreducible ways. Then there's a set of things that we humans sort of think about wanting to do. And that's a very small subset of what can in principle happen in the computational world, so to speak. I mean, just as the things that happen in the physical world, there are things where we can kind of understand from a human point of view what's going on, and things where just the waterfall is flowing as the waterfall flows following the laws of physics, but we don't have a good way to have sort of a way to sort of engage with human objectives and so on in what the waterfall is doing. We might attribute to the waterfall, it's trying to do this or it's trying to do that. We sort of anthropomorphize the thing. But I think the thing that I've been interested in is what's the bridge between what's in principle possible in the computational world and what it is that our civilization and our biology have led our brains to be able to think about and to choose to think about. And I think that's so I'm curious, in the world of fiction, you can kind of imagine extending. I mean, we have a certain set of things that we are used to in our current civilization, that we're used to, concepts that we're used to thinking about. You get.
Well, they're like thought experiments. That's the old phrase, where, like, if I want to know what it would be like if we had telepathy. And people have written about that, but I've been thinking about it more. And if you set up, I mean, futurologists like to say they're going to describe scenarios of things that could happen, but those are they're not very deep necessarily, the scenarios they're going to come up with. If you want a really deep scenario, you actually have to do a novel. You have to really immerse yourself and have people that are as realistic in it as you can imagine, based on people you know maybe, or like realistic people, and then have it be interacting and just watch it happen. And then keep nudging it in ways. I like to always, I once heard from Will Wright, the game designer, and he said, whenever you want to get from A to B, it never works. There always has to be something C that you have to do first, and then you might even be, before you can do C, you have to do D, and that's how life works, the plots, and that's.
One of the things that I find, as you're talking of telepathy, you're like, do we get to do brain-to-brain memory transplants and things like that? Do we get to, and I think one of the lessons of modern times is, this is another place where we need some kind of computational language. We need a symbolic description of the world, because your brain is going to encode knowledge in detail inside it in a way that's different from the way my brain encodes knowledge. So we kind of don't have this notion.
I was thinking about that, and that's where the life box could be something useful. This is an idea that we've both been thinking about making maybe a fairly, to begin with, a fairly simple digital model of your mind by getting, the database of everything you've written or said, and then generating as many hyperlinks within it as you can, and then having some good search engine, even a somewhat intelligent search engine that finds things. And so if you ask it a question, it'll spew out a fairly reasonable response. And I was thinking that if you're going to do telepathy with somebody, it would be good to have a life box as a sort of transducer. So you wouldn't go, in other words, when I was trying to feed something to you, it would go into your life box that would kind of assimilate it by your sets of associations.
Right. So it's like this is... to understand it, you have to understand it in the context of your life.
Exactly.
This is kind of a description. It's kind of that's the way of internalizing it.
The context, yeah.
Right. Of saying, because when you try and explain something about what's going on, it's not a trivial thing for the computer if it sees your life box and my life box and it's trying to align them. That's not a simple operation. You might have to unwind to the very beginning where we were both learning, the most elementary things. I just found my, I've been a human who's kept probably more data on myself than any other human, for better or worse. And I thought this was a completely de novo trait. I just found these notes that my mother made about me when I was up to 2 years old, which include precisely when I started saying each different word and so on. So I was about to kind of expose these things. So that will be the beginning of my life box, so to speak. As when did I learned the word yes before I learned the word no, which is probably a comment on my general personality or something. But it's probably deeply intrinsic. Yeah, right. It's something like that. But this whole question about sort of projecting what will happen. One of the things that I find really sobering is to think about technical innovations, even computational irreducibility, and say, so what does it mean? How does it affect the world? And, we're at this blockchain conference right now, and it's this utterly bizarre thing that computational irreducibility became kind of the proof of work idea.
Yeah,
it's just crazy.
Well, that's the thing. I didn't know much about it, and so the guy organizing it from IOHK invited me because he likes my writing. And then I said, sure, I'll come. I mean, you're going to pay me. I'll be there. And then I started reading up. I'd never quite grasped what underlay Bitcoin. And then there's this thing, proof of work. And I thought, they're doing something interesting, like finding prime numbers. But no, there's some completely cheesy encryption algorithm. It's called SHA-256. And you have to find a number. So if you put the number in with the code of the previous Bitcoin that was made, then it'll happen to be encoded in something that begins with 16 hexadecimal zeros or something like that. And I'm like, what? I mean, that is such a pointless problem, And the only way to do that is to search through a quintillion integers until you happen upon the right one.
Right. I mean, it's kind of like if you were imagining how would computational irreducibility be used in the world.
Yeah.
This is kind of the last thing I would think of about how it would work.
It's just dragging science in the mud,
Well, it's like I'm sure if you think about Turing machines or something,
Yeah.
and Alan Turing's original idea from 1936 of what it would be to be a universal computer, and then you project forward and you say, what were the first universal computers used for? Well, they were used to do things like store lumps of databases or used to make word processors, for example.
And simulating the hydrogen bomb, that was one of the very first.
Yes. Well, and attempts at weather prediction and things like this.
Weather prediction.
But in a sense, these in no way make use of the core idea of, you can program it to do anything. Because in word processing, you're programming it to do something, very trivial.
Yes.
And it's funny how but people wouldn't have tried doing word processing unless they'd had universal computers. It would have been too expensive to kind of imagine making something like that.
Yeah.
And I think that's to me, that sort of interesting thing is to think about, given these technical things that we start to understand, what will they actually mean in the world?
Well, William Gibson, the science fiction writer, has this saying, the street finds its own uses for things.
Fair enough.
Yeah.
I think that's also true of biological evolution. I was interested in, if you look at these different forms of organisms and things, you say, this is that shape because, and then you give some whole explanation. I had this great experience years ago. I'd been studying the shapes of mollusk shells, and I'd made up this kind of array of what all the possible shapes of shells could be based on some essentially mathematical model. And then the question was, do the mollusks of the earth actually populate all these possible shapes? And I went to see a curator of mollusks at a big natural history museum, and it's like we spend all this time, and he's pulling out each specimen and saying, yes, this looks like your particular pattern here. But then each specimen had a story. This one wedges itself in the rocks so it can get food there or something, and this one broods its shells and its eggs in this little cusp shape and so on. So. But then the bizarre thing was, at the end of the day, we filled basically every square, yet every square has a story. So I think it's the same kind of thing. In biology, what's happening is you're randomly generating these forms, and then these forms are finding uses.
Oh, the street finds its own uses for things.
Yes, right, exactly. So So I think it's true. Like other proteins that we use in our bodies, whatever it is, some number of tens of thousands of proteins, are these kind of random proteins that just got recruited because they were useful for some particular thing that we need to do, or are they proteins that were carefully crafted to achieve a particular purpose?
Yeah. And any molecule that has only a very few atoms in it turns out to be kind of important in the world.
Yes. Right. Well, it's the same thing with these simple programs.
Yeah.
Any sufficiently simple program has found uses. I used to my favorite cellular automaton programs that involve just rules for how you update arrays of black and white squares. There are 256 of the simplest ones of these, and I used to just have a file cabinet where I would file papers where people had applied different ones of these rules. And pretty soon, even rules where I could not imagine they would ever have an application. In fact, one of the ones that happened fairly recently was a rule 184. And Rule 184 I thought was okay, not my most exciting rule, et cetera, et cetera, et cetera. And it turns out it's the standard model for road traffic flow now. So it's and yet, it just arose originally by being rule number 184 out of an enumeration of possible rules.
Yeah.
But because it's simple,
not like good old Rule 30.
Yes, right. That doesn't. Rule 30 for road traffic flow. Rule 30 makes randomness all over the place. That would not be good for road traffic flow.
Those are the first things I programmed after I came to San Jose State and started teaching computer science instead of math. I was just teaching assembly language, and I would program cellular automata in assembly language because it was hard to get a computer to do anything at a reasonable speed then. And it was. I loved watching.
That's the real programmers program in assembly language. That's what people used to say, but I think mostly the people much younger than us, who are the people who are now kind of the up and coming computer science folk, they don't learn assembly language. They don't teach assembly language.
Well, I only learned it because they assigned me a class teaching.
It's kind of coming a little bit back. I mean, with the blockchain and cryptocurrencies, the virtual machines that actually run, like the Ethereum virtual machine, for example, it is, there's an assembly language there, and people sort of care about what's in it.
Well, those things have to be fast if they want to have scaling.
Well, it's the particular idea there, which is kind of a weird and crazy one, is you run the same program on every single node on the network. And that means that, and you also want to have something where there's sort of it's transparent and transportable what's going on.
Well, that's the whole thing of blockchain, that everybody has to have the whole database on their own device. It's bizarre.
Well, it's one of these things where it's because the cost of memory has come down, and it's one of those unexpected consequences. I mean, I think you were talking earlier about, why don't we just have the whole web on our computers? Absolutely, we can do that. It's not that big.
Well, I was saying that would be a way to kind of vitiate the insanely large power of Google if we each basically had the equivalent of Google on our phone in our pocket.
Yeah, well, the text content is maybe 10 terabytes.
Yeah.
So that's absolutely doable.
Yeah.
I mean, the thing that's interesting, though, is
you see the database is 10 terabytes?
The text content, so the images are bigger.
Yeah.
But the pure text
of
the, and you can argue about, no, it's not much at all. You can argue about, which web pages are interesting. Is it, 10 billion web pages? Is it, maybe 15 billion web pages? But there aren't actually that many web pages that are a human made this, interesting web pages. I mean, there are ones that are generated on demand from underlying databases and so on. That's a little different again.
Yeah.
But it's not huge. And in fact, it's interesting that even in, the data that we have for Wolfram Alpha, the numerical data about the world, like every weather observation that was made in history of that numerical data is bigger than the text content of the web. So in other words, the things that automated sensors have produced, and all the financial price data and all this kind of thing.
So pretty soon we'll just have the whole enchilada in our smartphone, though it'll probably be an intelligent slug or something you said in your talk today. I thought was fun, and I want to refer to that a little bit. Again, there's this thing about the richness of natural computation, and it's just as quirky and odd as a human can be if you really pay attention. Again, I always come back to the leaves in the wind. I just love looking at them shaking, and it's as interesting as listening to a lot of people talk. And then Stephen was saying, well, okay, suppose that we find this Lifebox style way of modeling ourselves and get the AI in it. So you basically have a pretty decent software replica of yourself. You could call it your soul if you wanted. And he said, so suppose someday there's all of humanity, we have 10 trillion souls in a box. And then he says the sort of deflating thing is that's really, you could just as well be looking at a pan of water that's about to boil and it's seething around a little bit. It's not that, big deal.
Yes. I think this is, in a sense, the story of science has been a story of discovering how not special we are.
Yes.
I mean, it's the one little thing that we still have, the one little special card we still are carrying around is we're the smart ones. We have this intelligence thing, and nothing else has that.
Yes.
And I just think that's not correct.
Yes.
I mean, I think we're no more. There's nothing more special about our. What's fundamental is this idea of computation, this idea of following rules a long way and being able to work out their consequences. And we have to compare. How do we compare our civilization to, let's say, geological civilization? The way that rocks have been formed on the surface of a planet.
Yes.
There's a complicated history. There are all kinds of interactions. There's all sorts of things that emerge at different times and so on. And we have to, we say, okay, we've got all this wonderful, culture that we've developed, and we've got all these different features. Compare ourselves to that. To the geology, for instance.
Yeah, I've just been reading a geology book, Assembling California by John McPhee. It's just, I never realized how incredibly rich and gnarly it is. It's just amazing.
But you see, I think that's the same kind of computational irreducibility story in the formation of these rocks as it is in the formation of our culture and our civilization.
Yeah, we think we're so smart, but we're just gnarly. I mean, I like to say the word gnarly, but like if you look at the root of an oak tree or a redwood twisting around, it's grown over years. It's been feeling its way and working things out.
Well, but you see, I think the thing that is people talk about, let's find extraterrestrial intelligence. How can we be the only example of intelligence? Here's my expectation. So we are developing at this point one example of alien intelligence, which is AI. That is our first, close at hand example of alien intelligence. And we can see that it has certain features that are hard for us to understand, that act in different ways, et cetera, et cetera, et cetera. Once we get used to AI, we will no longer be looking for extraterrestrial intelligence, because we'll realize that just these things that are just doing computation are doing something which is intelligence-like. And we'll say, well, actually, the weather is a perfectly good example of that. Geology is a perfectly good example of that. There's nothing really to find. I mean, it might happen to be the case that out there somewhere in the universe, there's something which has a more precise degree of alignment with our particular history. It got RNA molecules, it produced biological life, it did this and that and the other. But that would be coincidental, and it's not like it's the intelligent and the nothing. Mm-hmm. It's the many different forms of intelligence. Mm-hmm. And do you happen to be one that happens to be very closely aligned with our own?
So you don't just have to look at the sky and yearn for the day that we find something different. It's right here.
Right. I think so. I mean, we can just study the world around us to see sort of alternative forms of intelligence, which it sounds very, as you say, deflating to realize that that's. But in a sense, it would be very surprising if it wasn't that way. This would be the first example in all of scientific history where we were truly, truly special, and where nothing else like us was around.
Yes.
And the answer has always been in the past, actually, we're not really special at all.
Yes.
And I think that's what it's going to be in this
case,
too.
Yeah, and the sunspots, they're clearly an intelligent race,
Well, and I think it becomes it's sort of an interesting thing when you get to say, well, who's in charge? And how do we think about ethics for AIs? How do we think about ethics for the natural world?
Yeah.
These are things where there's a ethics for the natural world is not a trivial issue in today's situation, how should we think about that? I don't know the answer. I think it's
well, just to appreciate that these things are intelligent and beautiful. And I mean, some people, if they buy a property and there's a tree on it, their first impulse is to cut it down. It's so barbaric.
Well, but you have to take that point of view. It's at what point do you extend kind of our sort of appreciation and views about the sanctity of whatever it is, human life, intelligence, whatever. To what extent do you extend that?
Oh, to plants.
And at some point it gets kind of crazy because you don't get to change the world in any way. It's kind of like what people are talking about validation.
Live light upon the land.
Yes, right. But I mean, it's like what people are saying when you talk about, I've got a blockchain and I'm going to verify that it doesn't do anything wrong ever. What you realize is that which is perfectly verified, the only thing that can be perfectly verified is the thing that doesn't do anything at all. And so the only thing which can do no harm in this sense is the thing which does nothing at all. And I think it's sort of an inevitable feature of our existence. We're going to make changes to the universe. That's but I think it's a question that I've been very curious about. Is as we imagine kind of the trillions of souls in a box future for the human condition. First question is, what will it feel like to be one of those? And what will they do all day, so to speak? And
well, that's always the question. There's this idea that being in heaven would be very boring.
Yes, right. Well, this is as close as we're going to get technologically to the sort of theological view of heaven.
But they'll probably I mean, if there are trillions of human souls, they'll probably be hassling each other. I mean, if they're humans.
Well, right. That's one view, is that society is a key aspect of sort of the human condition.
And there's been, probably there would be some sort of scarce resource in there.
Well, right. I mean, this is a, that's an interesting speculation and claim that it is sort of a constant of everything, that there is sort of society between agents and competition for scarce resources. I don't know how general that is. I mean, that's a question. I tend to think that one of my more bizarre sort of conclusions is, if you are a disembodied soul operating in a virtual world, so to speak, you can be like in the Matrix or something, where you have something which is an imitation of the real world.
Yes.
Or you can say, oh, forget the actual universe. I want to explore the universe of all possible universes.
Uh-huh.
And so my kind of, I've been interested in sort of the basic science of what the universe of all possible universes is, the kind of computational universe of possible rules for setting up universes is like. And so one kind of bizarre conclusion that I'm not allowed to make myself is that maybe the future of humanity consists of people basically spending all their time exploring this computational universe of the same type that I've spent years exploring from a basic science point of view, that becomes the, that becomes the inexhaustible sort of adventure.
Oh, that's what the trillions of souls are doing?
Yeah.
They're looking at higher degree Mandelbrot sets?
Yeah, they're looking at all possible computational universes. It's like we've lost interest in the particular physical universe, and we're just going to explore the universe of all possible universes.
Well, yeah, it's still, the natural world there's things about it that just computational universe doesn't really capture what it's like to look at to go in the woods and walk along a stream and look at the
See, this I wonder about. I feel like one of the things that we've been successful at is seeing what the essence of what leads to that kind of richness that we see in nature is. Mm-hmm. The details, the detailed rendering, well, that's the specifics. Mm-hmm. But in terms of having something where we are generating richness, where the richness still makes sense in some sense. That is, the richness isn't random. It has a structure.
It's that level
to it.
Of complexity that we're always talking about.
I think that's something where we do have some hook at this point to understand what is the essence of what nature is doing.
Well, there is a sensual pleasure if you find a suitably gnarly cellular automaton. It's very pleasant to look at.
Yes, right. Whether that's because we're used to having evolved sort of around nature, and this reminds us of the essence of nature.
Oh, I think that's a good point. Yeah.
Or whether it's something more intrinsic to the way that our brains work, and they're trying to find order, but they find pleasure out of finding order, but having to do some work to find that order.
In a way, Stephen, we're like two souls in a box. We're in this room that's, my God, it must be 40 feet high and 50 by 50. There's no sound in here but the buzzing of the air conditioning fans. We're in the convention center of Miami Beach. We crept in here to get away from all the noisy humanity outside.
Yeah, right. So we're channeling that future. Yeah, I think. But one of the things that I wonder about is as we look to sort of the evolution of human purpose. That is, at this point, we say, we're doing this podcast because we think it's fun, because we think, maybe people will enjoy listening to it. We think, we've got a whole chain of stories about why we're doing this.
Yeah.
It's, as you observe, if we were to go back in history and we were to imagine, what's going on here from the point of view of somebody, 1,000 years ago or something, it might look pretty weird.
Yes.
And so when we imagine, the disembodied souls and what are they going to be thinking about and how are they going to feel about what they're, the sort of the purposes that they're following and so on, to
it's
us
always
now,
very. There's a human tendency always to think that we've reached the apex of civilization. As a science fiction writer, I have to spend a lot of time trying to look 20, 50, 100, 1,000 years ahead. And that's something the average person also doesn't do very well. They can't imagine that they will ever stop using the keypad on the smartphone, even though they've only been doing that for 10 or 15 years.
Yes.
It's just, we always freeze up at the thought that this isn't the coolest and best it'll ever be. But Yeah, I was saying a phrase I was using today a couple of times. When Stephen and I met, it was in our early years of bitter struggle. He was barely getting his ideas accepted. And I remember once you said, half of them say it's wrong and the other half say it's trivial.
Right.
And you said,
that's the academic way.
Yes. You said, that's a good place to be.
Yes. No, it's certainly, one of the things that in my efforts to kind of introduce new ideas, it's one has some solace and it thickens one's skin to realize that things where there is the greatest protest at the time when they're introduced are the things with the highest probability of having good long-term impact.
That is a good
people,
point.
People say, "Oh, that's just."
Well, that's happened when we started writing cyberpunk novels. The SF establishment. There was great outrage. These punks, these cretins, these nasty people.
Right. It's funny how new things happen in the world and what it takes for new things to happen in the world. And I think that's in terms of, thinking about the future and so on, and thinking about how does, is there always newness? Will there always be newness? Is there an infinite frontier of, so for example, one of the things actually comes back to the computational irreducibility idea. The question is there always more to discover? Or is there a point, like people said 100 years ago, everything that's worth discovering has already been discovered?
Yeah, they always say that. Yeah.
Right.
Yeah.
But I think it's interesting because what one realizes is that it's actually a theoretical fact about computation that there's always more to discover.
Yes.
And in like the cellular automaton, the game of life cellular automaton, that's now been sort of out and about for like 50 years, and it's interesting to see that there's more being discovered all the time. People have
just ask Gosper.
Yes, well, quite. Right, but what's interesting there, I was about to make a study of the kind of meta-engineering of life. That is, when we talk about microprocessors, we know Moore's law, which gives some kind of, sort of overarching statement about how microprocessors tend to get faster over time. The question is, if you're dealing with the raw bits of a cellular automaton where people are discovering that you can make things which act like circuits or things that do this or things that do that, and you ask the question, what is the arc of evolution of the technology? The bit patterns, you could have any bit pattern in the cellular automaton, but which bit patterns do people choose to use? Which is kind of the same sort of question as what do people choose to invent? How do we build our world based on what we choose to invent? We could have invented very different things from the things we've actually invented, and we could have, like for example, I don't know, we've got tables and chairs, for example. Those are concepts that sort of.
Well, there's always the feeling there's some simple tool that we never thought of yet.
Yes.
I have a friend who always says, he even has a name for it. He calls it the flick-it. It's like the screw or the lever, but somehow we haven't invented the flick-it.
Yeah, well, so that's an interesting, as you try and think about sort of what the world might be like, to what extent do you imagine that you can imagine, so to speak, things like that?
Well, it's part of it is just paying close attention to what I see every day, and then just say, what if I dial that up? What happens?
Yes.
A lot of it is just doing that. And then I do have this conviction that there is some really big scientific discoveries still to come, things that we haven't dreamed of. I still think that there might be some stuff going on at the subquantum level that we haven't taken advantage of. There might be some really cool stuff that could happen. I recently wrote a new preface for Infinity in the Mind for Princeton University Press. It's my 5th preface, so the book's done fine. And there I was speculating that how would it be if our physical world was like Conway's surreal numbers? In other words, what if it had the quality that not only was space and infinitely divisible, but you could go down Aleph 1 levels and Aleph 2 levels.
That's interesting.
And we didn't have to go out to the transfinite, and we've got these things right here. And then, so the world could be incalculably richer than we've realized yet.
It's that's the big question: is space ultimately discrete, or is it Is it a continuum, or is it, as you're suggesting, kind of beyond the continuum? So
they call it an absolute continuum. It's like absolute infinity. It's like the class of all ordinals, but it could be that.
See, my own guess is that we're being held up in the progress of physics by the fact that we assumed that Euclid got it right at the very beginning of his postulates for geometry. I mean, Euclid basically says, a point is that which has no part. In other words, he's kind of describing the continuum nature of space. And my own guess is that that's wrong. My own guess is that there isn't that worse than being in the continuum, where actually, the correct view of space is to be discrete. But that's an interesting example of what. So, I mean, if you try and follow that through, see, one thing I wonder about is let's imagine you follow that through. Do you end up with a consistent, conceivable universe or not?
Well, it always, again, I'm a mathematician, a computer scientist, so if I'm going to write about something, it's going to be consistent. And I'll just screw with it until it works,
But so in a universe that has that absolute continuum character, is it a universe where sort of communication works very differently from our universe, or is it?
These are questions I have to think about, but I haven't gotten that far into it yet. At the moment, it's just, partly it has to be a vision, and I can convince myself that it's true. So then I got that. I was on the beach, and I just started thinking, I mean, what if it's like, I was imagining it's like there's galaxies inside me. I know I just sound like a hippie here, but I'm not. It's just like rational scientific contemplation. And just that it's an interesting idea that you're actually as big as the universe if it's an absolute continuum.
Yeah, that is interesting.
Yeah.
I mean, I would argue the whole principle of computational equivalence thing gives us a certain equivalence to the universe, as in it's we're not seeing something very different. But I'm curious in this idea that you kind of just amp up something that is already sort of there in sort of the idea space, so to speak.
Yeah.
To what extent do you think that what's actually developed over the course of your life, for example, in technology in the world, could have been expected by sort of just the amping up of what there were already seeds of, and to what extent is it like utterly surprising?
Well, to me, the chaos theory and new kind of science were surprising. They were, for me, those were big changes in the way I viewed the world. That's why I value it. But there's so much more to say and will never be done. But
there are all kinds of interesting
We're two souls in a box in the outer reaches of the galaxy.
Yes. Yeah, right. But,
so, and we've got what? We've got 48 minutes. So that's probably enough. Maybe we'll do another one someday.
About a few interesting things.
Yeah.
We could talk about. I mean, I think that it'd be fun for me to talk about fiction, which I know little about, because that's and I think it would also perhaps be interesting to talk a little bit about sort of people and history and life trajectories and so on.
Yes.
Because that's we've seen and the trajectory of things like the technology industry, which is
well, let's do that again sometime. So I'm actually getting really cold in here.
Okay, all right.
So
time to wrap.
Yeah. So I'll say something, by way of farewell. So it's been great talking to you, Stephen, and illuminating. Likewise. As always. And
we have to do this again.
You got it.